All right, there we go. All right, guys. So today we're going to continue with machine learning on graphs with the topics, machine learning on graphs, and we're going to talk about graph embeddings. Now we're going to have a short lecture today, and you will learn more material at the seminar. So first of all, what do we mean by graph embedding? Well, it's sort of, very, very simple idea that for every node of the graph, we want to every node, we want to assign a coordinate in some space, right? And that's about it. So in some sense, when you try to draw a graph and you want to put nodes on the two-dimensional plane, you're actually embedding it into the two-dimensional space, right? And positioning, depending on what method of embedding you choose, for different nodes, you'll get different positioning on the plane, right? And sometimes you will actually nicely see the graph. Sometimes you will not be able to see it well because it might, for example, your embedding might collapse nodes all on top of each other. But that's literally the idea. Try to assign coordinates to every node. Now, if you assign, only one coordinate to every node, you're going to embed the graph into one-dimensional space onto a line. You assign two coordinates to every node, you will embed it into two-dimensional space or on the plane. You assign three coordinates, you embed it in three-dimensional place in space into the space, right? But you can actually assign 10 coordinates or 50 coordinates, or as many coordinates as you want to every node, and that will be embedding of that node in that space. Now, there are different names for this. Again, sometimes people call it projection, sometimes they call it embedding. And the other word for assigning coordinates is encoding, right? So the modern term that is used, especially with neural networks, is encoding. And so you encode nodes as low-dimensional vectors, right? Or project them. And important here that there's projection is into the continuous space. So, it's a coordinate, it's a real value. Now, the question is how to project, right? Now, if the objective is to draw it the best possible way, you might think of projecting in such a way that you minimize, for example, the number of intersection of edges. Or, you want to make sure, the points are spread evenly around. So there are different sort of objective functions that you can come up with. The one we're going to talk about today is related to graph connectivity pattern. And what we want is to project such a way that node connected by edges will project next to each other. So we'll preserve geometric relations. But the idea is also not to just preserve local geometric relations, right, which is nearest neighbors, but maybe there is possibility to preserve some sort of second order or even further order relations. And yet another term for this is representation learning, right? Because we're looking and learning new representation for a node. A node is a node in the graph, but we're representing it with the coordinates in this embedded space. And we select particular type of projection, right? And then we apply it to all the nodes. So each node is projected independently from another. So that's what graph embedding is. Here's an example. Again, it's assigning coordinates to the node. This is, favorite karate graph that we looked looked at before. I've shown you many times this graph. Typically, the layout was designed by it's usually sort of the spring-based layout, for example. This one, the one you see here, is a layout done by DeepWalk. It's actually, again, assigning to 2D. If you notice, it's kind of nicely, does the grouping of the clusters, right? So it's kind of, it preserves clusters, so it preserves local information. So the simplest projection that you can think of, and the one that, in fact, probably previously considered, is by using single value decomposition, or sometimes it's also principal component analysis projection. The idea is that we can take the matrix and factor it out, right? That's why it's actually also called matrix factorization type of approach, and we briefly talked about it last time. Imagine that you have that we have an adjacency matrix, and here it's just shown for m by n, but it's square if it's the adjacency matrix, and you can actually write this matrix out as a product of three matrices, U, S, and V transpose. And this factorization is called single value decomposition, right? And the way to understand this is the following, the way it works. You can take here one vector, vertical vector, right? Then the S matrix is the diagonal matrix. I'm just reminding you guys, single value decomposition is the diagonal matrix. And then you can take the elements from this V matrix. And what happens is you multiply column vector by row vector. It will actually gives you matrix. Now you multiply this column vector by row vector, you multiply it by the scaling factor, which is the diagonal on this signal matrix, and it gives you some form of A. So if this is kth vector, we'll call it A, or actually let's make it I, call it A sub I. And in fact, the entire matrix, right, can be written as the summation of this type of products. Now, why are we talking about this? Well, because you can actually interpret this as an embedding in their space, because you can think about, for example, these vectors as being coordinate axis, right, as being axis, and these numbers that are here as a coordinates in this vector space. And what's interesting about SVD is that if you multiply all the way through, you will exactly reconstruct the matrix. But if you just a few of those columns, then you can build an approximation. And so if I take some, not all of them, but from A to the first column to, let's say, the case column, I will create the approximation A sub K. And it can be shown that this is the best in terms of norm approximation, right? So this is the best approximation overall to the matrix A, right? So in fact, you can think about this as embedding the matrix, right, into this low dimensional k-dimensional space where there are k vectors, and these are the coordinates for the embeddings. Now, remembering that A, if A is symmetric, it can represent a graph. This is instantly assigning coordinates to a graph, right, to the nodes of the graph. That has been known for as many years as PCA exists, right? Just probably more than 50 or even more. Now, next method of projecting is actually much more powerful than just using SVD, but it is very much connected to it. And in fact, we already learned it last module when we talked about spectral clustering. I'll briefly remind you the idea. When we talked about spectral cross clustering, the spectral graph partitioning, we said, okay, let's say we have a bunch of nodes and we want to assign labels to the nodes, +1 or -1, which class they belong to. And when we do this, right, then we can actually calculate the value of the cut, which is how many edges connects plus and minus class. And we kind of put it this way as Si minus Sj, where I and j are the nodes connected by an edge, right? And then we worked with a sum and came up with a formula, and then we converted this into optimization problem by replacing those s's with real values x, and solve. And that would help us assign nodes to the clusters. Now, what's interesting that if you kind of look at this and you think for a second like what we have done, what we've done is we have replaced those labels, right, s's that are zeros and ones, with x that is belongs to r, which is real value. And so I could just put here xi minus xj. But then what it is really we gave those nodes coordinates. Yeah, this is x, and again, this is x. And so we're not just giving them coordinates, we're looking for, we're summing the distances between xi and xj and squaring them and going over all connected nodes. So what this does is says, look, find, and then because it's minimization problem, right, we want to find those x's. Well, what it says is really to try to put the connected x's next to each other, because if you do that, the sum will be small. Now, we also talked about this, that of course the minimum here is put all the nodes into one point, and then the minimum is 0 here. But to prevent that, we're saying that, look, that the solution is not acceptable. Let's look for any solution except putting everybody to the same value, to 0. So, in fact, when we solve for graph Laplacian, we could have taken those values, eigenvectors, right, the values in the eigenvector, and use them as a coordinates. For particular graph Laplacian solution, it's just we use just one dimension. We use second eigenvector, but we could use second and third eigenvector, second, third, and fourth eigenvector. Then those eigenvectors are orthogonal, and so then we could actually embed a graph into either 2-dimension, 3-dimension, or any other dimensional space, where that space is defined by the eigenvectors of the graph Laplacian, right, of the Laplacian matrix. To sum up this approach, is what we're really talking about is the following. We're saying, okay, here is xi and xj. These are the coordinates for 2 points, the coordinates that we assigned to the graph nodes. We're gonna add them up with some weight, and we sum up only those coordinates, only those nodes that are neighbors, that have edge between them. And so here is this combination, xi and xj are coordinates of the nodes of the graph, aij adjacency matrix. So if they're connected, then there is a contribution to the sum, and if they're not connected, then there is not. And from here, it's clear that if this is an energy for the graph, energy for the embedding, then putting neighboring connected nodes next to each other, embedding them in the space next to each other, where the distance is calculated as just Euclidean distance xi minus xj, is a good idea that will minimize the energy, right? And this difference can be written as, in terms of using Laplacian matrix, where this is Laplacian matrix. And then, we're looking for the minimum of this u from x, and that will give us, in this case, one-dimensional embedding will assign nodes coordinates along the x-axis. If you want to go for higher dimensions, no problem. Just instead of xi, xj, you put here matrices xi with xik, and instead of just simple sum here, it just goes for the trace. And then we have to do some constraints again to prevent collapse of all the nodes onto the same point. And so this is a spectral embedding, graph Laplacian embedding, so it has very many names, and it actually works not that bad, right? But the idea is, again, every node getting its coordinate, and here we're explicitly saying that we make sure that xi that nodes that are connected, right? That they're connected because of aij, the nodes that are connected being projected next to each other, living next to each other in this in this space. Now, this is an optimization, and so we're trying to optimize, right? We cannot guarantee that this is going to happen, but the function will take a smaller value if we manage to find those locations, right? And here is an example of that embedding again for Karaite graph. Here it's shown with two clusters, but that's what it looks like, which is actually also not bad at all. Okay. So those two methods, they're kind of old methods, if you wish, that has been used by the graph community for quite a while, and in particular it has been used for drawing graphs, because drawing large graphs is not easy, and those methods were quite popular to draw. Now we want to generalize this and maybe try to kind of expand this in terms of the information that we preserve. One thing that I also want to mention, that in this slide and in this projection, right, in this approach in spectral graph projection methods, we're only taking information about neighbors. So it is nearest neighbors information, right? That's the information that's being used to project. Okay. So let's see how overall embedding concept can look like. So we have a graph, right? And then we do map it onto some embedding domain, right? And this mapping, you can call it projection, you can call it an encoder, and you get those vectors. Now, overall, the idea is that when we do this mapping or this encoding, we want to make sure that the certain property is being preserved. For example, we want to say that if the two nodes are next to each other in our original graph, then their projection, the points that we get, will be next to each other in this embedded space. Or we can say, look, now this is sort of the minimum amount of information. Or maybe we can say, look, there is this node, there is this neighbors, and then there is this nearest neighbors. Okay, please preserve that. Make sure that this node and its neighbors and its nearest neighbors mapped into closed locations to each other. Or maybe we can think about the structural role, the centrality metrics of the node, that they will be preserved. That nodes with the same centrality will be mapped onto the same location in the embedding. Or maybe the structural role in the sense of remember structural similarity, that structurally similar nodes will be mapped into the same location. Or maybe we want to preserve community structure, and that means the nodes that are in the same community, in the mapping will be in the same community. So how do we check that? Well, the idea is that we can actually come up with some sort of metric that we use on the graph. Then we do the mapping. Then we try to use the same kind of concept, the same kind of similarity on the mapping, and make sure that those metrics, whether it's done on the graph itself or if it's done on on a projection, will give us approximately the same result. Of course, you might want to learn to completely reconstruct the graph from the embedding, but that is it's probably not going to work, because then you'll need to encode too much information, and the embedding is quite often compressing, right, information. So it's less from original data. So we want to learn those encodings, as I said, and the encoder maps the nodes to the embedding, right? And let's say we select one particular similarity function, and let's say similarity in our original network is whatever we choose, but we can, for example, select similarity as just being nearest neighbors, or being sort of on the same neighborhood. And in the projection world, right, in the one where embedding world, in the embedding space, we try to use dot product as their similarity. Here is shown the dot product. Why? Well, because of course it's very close to Euclidean. The idea is when you have multidimensional space, and we're comparing vectors, it's probably better to look for angles in between vectors, and so that will tell us that okay, two nodes are similar if the cosine of the angle in between small, which is a dot product, right, and they're dissimilar if their angle is large, dot product is small. And so we're gonna want to project the nodes, then measure this metric for the nodes, right, as a similarity, and we want it if the nodes, original nodes, are similar in some way in graph, then their projections will be similar in the embedded space. Does this make sense? Okay, so this is a concept. Now, what do we do with this concept? Well, here comes the method. In fact, it's a class of methods. It's called random walk embeddings. There are three popular methods. We're going to talk about one of them today. So the original walk embedding. So the idea is the following. We want to be able to sample some of the connectivity in the graph. It's very hard for every node to actually use all its connectivity information, simply because if you want to take a node and calculate shortest path, for example, from this node to all the other nodes, right, we're going to get in a lot of computational problems, right, a lot of computations in there. And in fact, it might be an overkill, right? For each node of the graph, calculate all the say, for example, shortest path for this node to every other node. What we want to do instead is to just take some neighborhood. Of course, we can use like breadth first search, or depth first search. Here is the idea to add a little bit stochasticity. And again, the reason because breadth first search or depth first search, if you have a graph like power law graph, it actually grows extremely fast. And so within a few steps, as you remember, you'll be covering a lot of graph. And so to avoid that, instead, we can actually just create random walks. And we've done random walks before many times. So, you pick up one node, you start from the node, you run the random walk, then, you pick up that node again, you run the random walk, you pick up the node again, you run the random walk, etc., etc. And so what we want to predict is that if we take two nodes, U and V, then they will occur on the same walk, right? U is a starting node, V is a node in the random walk. Of course, we don't want to have very long random walk. We can say, okay, random walk of 10 steps or whatever steps, and then we actually run those random walks and see how often it ends up on a particular node. Obviously, the nodes that are nearest neighbors to your selected node, to the node U in this case, random walks will, random walks, of course, will more frequently visit these nodes than, say, for example, that one, but they will still visit it. And so what we can do is we can estimate just by running those walks, like literally running those walks, is we can estimate the probability of ending on the node V if you start the random walk from node U. And you can do it for starting those random walks from any nodes. Then the idea is the following. Then if we map those two nodes, right, onto some points in the multi-dimensional space, let's say this is two-dimensional space, and these are the projections, right? Those are 2 points, those are projections. If this probability is high, because the nodes are next to each other, we want this angle to be small. Or if we take, for example, this node and say some other node here, and let's say the probability is low, then we want those two vectors, embedded vectors, to be far away from each other. So we want, the dot product in between those two vectors, the embeddings will be proportional to the probability of starting from node U and ending at node V. So that's really the idea. Okay. So how do we do this? Well, we're given a graph, and our goal to find this embedding, this projection, or if you wish, you want to find a function that takes our node and maps it onto the coordinates, right? And as always, instead of just doing the probability, we would rather do log likelihood objective, right? So logarithm of probability. And since random walks started from all the nodes are independent, right? We can multiply the probabilities, or we can sum a logarithm of probabilities. So we sum over all the nodes on the graph, right? So we start random walks from all the nodes on the graph, and M sub R is a neighborhood of node that being covered by a random walk. And this is the embedding of that node into our multidimensional space, the one that we want to find. And so what we want to do is we want to maximize this probability over all the nodes that we have. All right. So this is this value is obviously a model prediction of probability of visiting node in the neighborhood of node U. When you graph, given that you're starting from node U, and this is embedding of that node. All right. So given the embedding, predict the probability of visiting the actual nodes around that node in the graph. That's a problem setup. Now, well, you can reformulate it. If you look at this value, you can reformulate it by, instead of just doing their probability of neighborhood, right? Neighborhood meaning going through all the paths in that neighborhood, and that's what this says. And this is the sum. Now the question is, how do you define this probability? And here is sort of a little bit arbitrarily idea, but that idea makes things work, is parameterize the probability using what's called softmax. So the idea is the following, that if you take dot product, we want to make sure that we can sort of amplify the distinction, the difference in between the vectors that are next to each other versus the vectors that are further away, right? So we want this to be much, much larger than that. But if we just take cosine similarity, this is not necessarily the case. So we want to kind of make it much sharper than the maximal. And to do this, instead of just looking at the say value x, to make things sharper, you can actually look at the exponent, right? E to the power of x, right? To make things, will amplify the effect. But that, of course, cannot be thought of as a probability. So instead of using that, we need to take that exponent and we need to normalize it, obviously, over all possible values, over all possible points that we have there. And then if we do this, then we can put it in here. I mean, it sounds good, it sounds reasonable, but there is a problem here. And the problem is, if I just, as I just described, if I put in those values, then what happens is, actually, let me go back here. Notice that we do have summation here, and we also have summation here where we do normalization. So if we put this whole thing together, what we get is, yes, those two sums, it sums over all the nodes. Then here would go sum over all the random walks that originated from each node, right? This is every node in the graph. This is a neighborhood of every node. We're summing over, right? Because we're visiting all the nodes by the random walk, and this random walk again can be a few steps away. But then right here, we again have a sum over the entire graph, right? And that makes it instantly quadratic. And that because, here is the sum and here is the sum, makes it, it's quadratic. And that for large graphs is not going to work. And so the idea that the authors of the paper for the deep walk came up with was, so instead of just using that sum, produce what they call negative sampling. So instead of actually summing over all the possible values, they proposed to sum only over some number of nodes that are not connected, obviously not connected. And then this is a negative example. Now, I would send you to read the paper to understand why the sampling work. Sigma here is the classical sigma, which is 1 plus e to the minus x. This is a way to write this expression. And by doing this negative sampling, by selecting subset of nodes that are not connected, we can, instead of normalizing over all graph, we can normalize over them. And if we do that, we're instantly getting rid of double summation. Instead, just summing over some number of example nodes. After we've done that, look what happened. That's the function that we want to minimize. And I should probably write this lambda of z, right? Z is a projection, right? These are coordinates that we're looking for. And so what we want to do is find the minimum based on those z's. So how we do this? Well, numerically, we just use gradient descent by by changing z's such a way that on every step, we decrease value of lambda. So we're going to the gradient of the decrease of value of lambda. With this function, it's very easy, since it's exponents, it's very easy to compute derivative. so we can actually calculate the gradients and then use them to descend. Since this is quite large and we want to have stable solution, typically we use stochastic gradient descent to do this. All right, so that's pretty much the original paper by Pirozzi and his co-authors, and that goes back to 2014. Now, since then, there have been like lots and lots of papers proposed. If we're going to talk about this curves preserving methods, the one that preserves their structure of the name, that they are like random walk embedding based. This is deep walk. This is also node to back method, and then there is this methods called line. These are sort of the most well-known algorithms. Now, there are more algorithms has been proposed that will preserve or try to preserve, for example, the centrality of the nodes, or the clustering coefficients, or for example, the fact that the nodes belong to the same cluster. So that's pretty much it for this lecture. And today in the seminar, you'll be able to practice, I believe, deep walk and node to back. And with this, we're done. Any questions?